Hello everyone, welcome to my shop. I'm Robin, and today we're going to look at the design and construction of an attachment to do chamfers using a Dotco 60,000 RPM air tool. My son said, "Hey Dad, I got an idea for doing chamfers on here. We use the air tool all the time. We have two of them. Is there some way to hold this thing at a 45-degree controlled so that we can, bust chamfers on our work quicker?" And I said, "That's an excellent idea. I think we'll pursue that." So that's what this video is about. I'm warning you now, this is not professionally done. I didn't intend to actually do a full YouTube video of this. I didn't really have time for it. But I got part way through and said, I better cover this. So this is pieced together from videos I did for Instagram and different things. The audio is going to be crappy in certain parts and all that, but I figured you'd rather see it than me not post it, just because the video is not the best for its quality. So there's things that are missing. Every single detail is not covered in the machining of this, but I covered some of it pretty extensively in the platens and things like that. First will be the design aspects, and then we'll show some of the machining, and then at the end I'll show some of the rebuilding and tweaking of this. This was a original air tool that I had from way back, and so I'll show some rebuild and making new collets for this and some of the considerations involved in that. So let's cover some design aspects. I said, okay, let's use a standard cylindrical burr, but we need to put an outboard support bearing on that, because the bearings that are in this are way back here, and out here is where your workload is. So these things have a tendency, if you're trying to rigidly hold them, for this to vibrate and carry on. Even though the power's there, the rigidity of the spindle's not there. So by putting an outboard bearing on here, we're supporting this, we're making it run concentric, run more true, and we're getting rid of the loads here, so we're actually supported at two ends with the cutter in the middle. And you'll see where I had to do some tweaking on this and in the rebuild to get the collet to run nice and true, so that we didn't have a lot of run out here. And that run out would make the finish of the chamfer not be as good, and you'll see in the video the finish on these chamfers is ridiculously smooth for the feed rate that we're doing by hand. So how do we achieve the adjustability necessary and be able to use the full face of the burr? Since a very small portion of this gets used, I only tend to be able to go up to maybe 40 thousandths burr or chamfer sizes on these. And so there's the ability to use multiple spots on the burr by moving this point of cutting axially on the burr. So that's what we've provided here. And then I wanted a very simple means of adjusting the chamfer size. So this is the simple means I decided to use for the chamfer size adjust, and that is to have this gap control the chamfer size. And of course this gap will be the square root of 2 times the chamfer size difference. So these steps are actually 7 thousandths and a tenth steps difference in height, but they create a 5 thousandths difference in chamfer size. So this gauge goes from the 5 thousandths, 5 thousandths, 10 thousandths, 15 thousandths, 20 thousandths, 25 thousandths, 30 thousandths, 35 thousandths, and 40 thousandths. So you just loosen the screws of the second one after you've got this one positioned, and slide this into the one that you want, and then hold it tight against there and tighten the 2 screws. So not super easy, but also you're not fumbling around trial and error on what chamfer size you end up with. And then this is for 2.5 thousandth increments. This is just the still 5,000 steps, but shifted 2.5 thousandths. So we're going 2.5, 7.5, 12.5, 17.5, etc., etc. And then this platen design with the grooves, sharp-edged grooves, and very narrow bands that it rides on is what I did for my chamfer meister, and this works extremely well in allowing places for the chips and things to fall and get out of the way. So instead of riding on the chips, because this thing basically just makes a million little chips, it's throwing them everywhere, this needs to be able to plow through there and just scoot them out. And also the chevron pattern here, as you're pulling in this direction because you want to be conventional milling, or it'll run away on you. This actually sucks you into the corner. As this travels, you can see if you're stuck on here, you're running in. So this is actually pulling you to suck onto the corner. And then ergonomically, I looked at this and said, okay, this will work, or two hands, whatever, but this is easily controlled. The key here is that the air tool is so light and easy to manipulate with the small air hose that it's easy to feel this seating on your part. So you seat on one edge and get started, and then once you're on both, the same technique as using a wood plane, where you seat on the front as you start and then you seat on the back as you leave. So pretty simple.
So here is how I started the design process. I measured the Dotco tool and modeled it, including the burr, the modified burr. On the end here, I've modified the burr to have the bearing be able to sit here. Just one thing that I see a lot of people do modeling wise in solid modeling is they'll model this out of like all different kinds of extrusions, and I always find that whenever possible, doing things as a revolve allows you to put all of these details into the sketch in one place and be able to modify these things, change them, use configurations to make variations of it, and it's just a whole lot cleaner type of build of something. So in my mind, if it's round, it's going to be a revolve almost, period, never just a circle that's extruded. That was free. And this is a multi-body part, so I'm taking this. Next thing I do is I modeled the another revolve, which is the bearing on the end, so I know what I'm working with. This gives me my starting point, and then I take the this and I actually model my externals on this. And one thing you can do is to do a section view while you're doing this, so you can see what's going on as you model. You can see here, this was the important part. The bearing, support bearing, and the spindle's way back here, and you can see that from that distance and all this overhang and this skinny neck and this burr, there's no way that this is not going to be flapping in the breeze. And that's what this bearing does. It doesn't have to do a lot, but it does really stabilize things. The other thing is that the air tools in general, industry considers 3000s run out on these things good, and 3000s run out in my mind is not good, not for what we're trying to do here. And this very low run out that you'll see me get at the end from rebuilding, grinding the collet taper, and making a new collet, and then also lapping the threads of the collet and the collet seat to get the thread influence out of the collet, is what lets this get down to, like, 2/3 run out here before you install this. The other thing to keep in mind is if you have 3000s run out on this out here at the end, you're stressing this bearing. It's fighting to keep this thing bent in location and is getting cycled at 60,000 RPM, and it's going to tear that bearing up in short order. So this very low TIR is important. So now we'll carry on with doing some of the cuts. This is the clearance cut to get room to have the platens in here, and then we do some other cuts, and looking from the end, we come up here and we can do from this end and look, and you can see that now we're leaving our places for our we'll go like this. We're leaving our places for our dowel pins to go. And the other one is a little bit different. That one is, because we're working on a larger diameter, it had to be a different section to have these tangent. And then we'll go to the back here where you can see where we have these ears left for the pinch, and then we do our pockets for our counter bores and do our holes. And there's how we have modeled that part in context. But this is a single part, but it's a 3-body part. Then I will take this and we'll go to the assembly and we'll model the other pieces. Here you can see in this model where by moving both of them you can work different sections of the burr. So you get a lot of areas to be able to wear out a section, then move over, wear out another section, all the way across. You could keep a section of it for plastic so it's nice and sharp, keep a section for hardened steel. I haven't tried it on that yet, but I'm pretty sure it will cut it well. And a section for just normal, and a section for aluminum if you wanted to get carried away about it. But as we all know, once you cut with this burr, if you cut iron or steel with it once and then go cut plastic, it won't cut it quite as cleanly. So leaving a section that's for plastic only wouldn't be a bad idea. So that's the whole premise there. To be able to get this movable area of use rather than moving the tool in and out, because we've got the support bearing that we have to contend with being supported, we can't really move the tool in and out, even though that would be a first thought, is to slide this thing in different locations. So that's where I came up with the idea of having the 2 dowels and the pinches. And as we discussed, the ribbed pattern really works well on these type of operations. So that's just the general modeling showed you there to give you an idea of how I went about modeling this thing. And then of course I went and made rough drawings to work from.
Here's my working drawing. You can see the ears that are on this. There's ears on this end for the pinch. This is what this looks like at the end. This is the ears that are left on the main body back here. So all I'm concerned with now on the lathe is these bores through here. I'm doing these 3 from this side while I'm gripping here. I'm doing this. So there are all the bores are done, all this outside's done, this is all polished up, ready to go. Now I'll take a 7/8 collet that grips across these 2 together and do the other end. Here's the other side with the 2 flanges left on and the bore for the bearing. So I finally got back to the milling work on this for step 2 on the Dotco Chamfer Meister. So here we've removed those circular flanges to leave just the bosses for the socket head screws and the bosses for the dowel pins that hold the platens. Now this isn't a watch.
Really? That's not a watch. Wow.
But it's not cheating by glass beating it and covering up a multitude of sins. And since it's got a lot of handling, this is a lot easier to clean than glass bead. Since I didn't take any video of the milling on the main body of the tool, I'm just going to show you a little mock-up here of how I accomplished this. These 2 parallels here and here are an 1/8 inch difference, as is the 2 diameters, these main body diameters in each section. So using that, I was able to just grab this axially and move it to particular locations. So first I would put a flat on the top like this, which was tangent to the diameters that were in between the flanges, just as a angular reference tool. Then with that, I was able to set this angle with an angle gauge to set this angle to mill this off on this side, and then obviously flip it, mill these off on this side tangent, and then in between literally just eyeball and mill off, eyeball and mill off all the way across the whole thing to mill this roughly round, and then file in between, just file all the facets off to be tangent to the rest of the body. And the same on the other end. The only difference with the other end was that I had made these outside radii are an 1/8 inch radius. So I took a 1/4 inch dowel pin, hard turned it down to an 1/8 inch to fit into the holes that you saw me put in with it sticking up vertically. And then I could indicate across the top of this and across the top of this to get the angle, be tangent, and then just take the end mill tangent to the top of the part, run right off the side. So with that, I was able to do all of 8 locations of this, and then actually put the 2 filing buttons in. I made 2 to go in each location, and I put the 2 filing buttons in, and go ahead and file right down to the filing button. And since it's hard, the file just skates on the filing button once it gets there. It helps you put a real nice radius on. So that's how I did those ears. I just didn't want to leave that out because that was one like missing piece.
Grooving the platen face for the Dotco Chamfer. This is the large platen. So it's sitting at 30 degrees. I have an 0.45 wide woodruff cutter. I've only held about by 5/16 of an inch here. Don't ever try this with an ER collet, but with the R8 style you can get away with it if you're careful. And just use incremental Z moves down here to leave a 20 thousandths wide land with a 45 thousandths wide groove. Using the Brown and Sharp Precision angle blocks for setting the angle. Not that it needs to be precise. Flip the other way for the small side. By planning ahead and thinking about doing both pieces in this so that I'd have something to hold on to do the grooving in both orientations is a big plus. Now I'll saw the pieces out. I needed parallels that were 15 thousandths higher than my 1 5/8, so just 4 pieces of 15 thousandths brass shim stock that's been pressed in the vise to make sure it doesn't have any swaged edges, and tap the parts down and ready to go. Here I have both pieces together on their face, and I milled all of this excess material, leaving these pillars and putting this pocket in. With multiple datums on the PT855 readout, I have a datum on this side, number 98, a datum on this side, number 99, and then all the rest, heights and everything, I make the same. Therefore, I can do drawing dimensions on this one and drawing dimensions on that one separately. It also has tool diameter compensation, and you can go radius plus, radius minus, or on center. Here I have the drawing folder to show you how they're sitting in the vise.
Here I'm surface grinding that entire amount off the top, held in the magnetic V-block. This is a piece of aluminum tape put on the edge to be able to nick it before I touch the other wall. It just gives you a few thousandths of room to know when you're touching it. This block is carrying the lines of flux from one side to the other through this piece. Without this, this would have hardly any grip at all. So very important to think about where the lines of flux are crossing from this face to this face. Make sure that it's got something to carry it. Just using a scale to measure when I'm done. Same situation as the last one, needing a flux carrier. Hold the piece still. Check, it's good and solid. This one's down in the vise, so I have to check it using calipers to be able to get down in there. Can't lay a scale across the top. Last setup doing the top of these. Got the end block on there to resist the axial forces. They're indicating in the 2 pieces to be on the same level on this face so they can do the top drilling in both of them at the same time. Spot drilling first, then we go to the tap drill, staying off the bottom so we don't break through, and the body drill. Just spinning a 5/32 end mill down to 145 with just some back taper. Just a cylindrical grind with a taper, just using the face of a 600 grit diamond wheel on the D-bit grinder. Counter boring with the tool that we just made. Tapping, holding the top of the tap in the drill chuck lightly, and then just spinning with the knurled ring. Quick sharpen of the 1/2 inch diameter, 1/32 wide woodruff cutter on the D-bit grinder. Using that woodruff cutter to slit through the ears for where the pinch will grab. You can see the little dimple there from the drill, which is fine. There's our slits, but not all the way through to where it would interfere with the drilling and reaming the hole. Counter bores, now we'll just bottom tap these. There's the relief cut for the cutter clearance.
These have been reamed now. I have a 4,000th plastic shim here, and it's resting on this edge, and I have it blocked with a piece in the back. And we're taking, well, from 0 to 4 in that distance.
Just grinding off the top surface there, obviously at high speed.
Same thing with the 4,000 shim in the back, and just cleaning up. Here's the gauge is roughed in. There's all the swarf stuck to a magnet. It's all steel.
I have the two parts stacked together here, and I'm plunging down through. It's very important that the part is about a ½ inch behind the wheel. That's the only reason those things are behaving. If that was on center or in front of the wheel, that would be a crash. So be very careful attempting this. Going down to the bottom, now reciprocate at the bottom. Opposite side, same procedure. Going all the way down to the bottom, then reciprocating. Gives you an idea of how low energy that is to be able to leave that pillar standing up in the middle there. With better coolant flow, none of that would be burnt.
You saw me grind both of these together to the thicker version, which is the 5 to 45 thousandths and 5,000 steps. Then I put this one on the fine pitch chuck, straightened it, and then ground this down from these thicknesses down to the one that starts at 2.5 and goes in 5,000 increments. So 2.5, 7.5, 12.5, 17.5, 22.5, all the way up in that realm. Bearing spacer grind. The rotor needs to be shorter than the stator, which it is already, but you need to centralize it. So there's 1,000th and 8/10 on each end to keep it central. So I'm zeroed on the rotor, which needs to be 1,000th and 8/10 lower, and you can see here I have ground that inner race spacer until I'm getting that. So that's plenty close enough. Here's the front bearing end. These are class 5 ceramic ball bearings, grease lubed. This is the spacer that I ground to get the axial location of the rotor correct. And then down here, this Belleville spring goes in here and loads the outer rates to pull in this direction so that the bearings are preloaded. That bearing has to be pressed on just the right amount that it's just using a portion of the spring travel. Lap the stator ID for a smooth finish. Slots in the lock nut and a new lock nut wrench. Getting the spindle on center line so that when I tilt this to the 4 degrees to grind the taper using the Bridgeport as a grinding spindle, that I'm on center in the Y-axis. Trimming in the 4 degree on a side taper angle of the collet seat. So I've ground this collet taper running on its own bearings, and we've got it to an acceptable level for a air tool. So several tenths, even if it was 5/10, it would be plenty good. The only problem now is the collet has 1,000th and a half run out in itself, so time to make a new one of these. Cutting the 4 collet slits. End stop in the collet allows doing 2 at once. Might as well. It's almost a free part. Wrench flats on. Parted in half. Deburred, abrasive, bristle brushed, and ready for heat treat. Hardened with a torch. Now time for temper. Temper on the hot plate at 700 degrees. Get down to the tougher range. Needle eye lap to do the bore.
That's a lap gauge fit on the carbide pin. Pretty good fit with the paper. Sawing off on the D-bit.
5 times diameter from the collet nose. That didn't happen just after the grind. The threads influenced this. I had to lap the threads a little bit under load to get this to run like this. Thread eccentricity can influence the collet seating and force it to run out, even though the taper and the ID are perfect. Another part of the puzzle, grinding a bearing fit on the end of that carbide burr that's concentric to the shank within a few tenths. Using the piece of cold rolled steel there on that flexible piece of tape just as a pivot, and this bar is just some mass to lean on the flexible mandrel there, because without it they have a tendency to chatter, and they can actually vibrate and then beat the diamond wheel, the resin bond diamond wheel, and chew it up badly. So that's just to stabilize it, just enough mass there to keep it from resonating. Pretty big hint here on where I'm going with this.
Nice chamfers. Really smooth.
There's the chamfer quality. With that super low run out of the tweaked Dotco and the support bearing, it leaves an insanely smooth finish with no secondary burr.
Here's the sharp edge block. Now we're going to chamfer with a 15,000 chamfer. There's our chamfers. This section of burr has been used pretty much. There's a little bit of residual edge burr there, but that's how it's used on a piece that's handheld instead of the large pieces where you're moving the tool completely. There's the edge quality on Delrin, and that's with a fresh burr area.
Thanks for watching. If you enjoyed this, please subscribe, comment, and share.